I've just begun to develop this appreciation for Ohm's law. It's so simple that these things are linearly related, the voltage, the current, and the resistance. V equals IR is as familiar an equation as F equals MA. And I can use it to spectacular effect in all kinds of electrical technology. We've already engaged in some simple problem solving where there's just a resistance, a current, and a voltage. But as you know, our electrical technologies have become very complicated indeed. In the early days when these things were first discovered, everything was clunky and large, but we've miniaturized everything. We've created a larger level of sophistication to the point now where we create electrical circuitry that's microscopic and all spectacular achievements. Well, we'll never get there in this course because we have other things to discuss. But I'd like to take one step in that direction today by suggesting another level of sophistication. I've already looked at electrical circuits that have one resistor in. What I'm going to do today is consider circuits that have more than one resistor. It turns out there are two basic ways that I can add resistance into an electrical circuit, and we'll discuss both of those one at a time. The first is the series combination. A series combination looks like this. You see my familiar circuit diagram stuff. Here I have a 9-volt battery, and I have a 1K resistor. And I'll just remind you that that 1K means 1 kiloohm, which is 1,000 ohms. And that's fine, I've solved that problem. But now you can see the twist that I put onto it. I've added another resistor. Not only have I added another resistor, but a resistor of a different value. So one resistor and another resistor connected in. Now that complicates the situation, but as you'll learn today, it's not terribly complicated. I just have a new rule that I need to understand. By the way, always bear in mind that these circuit diagrams are really just schematic. They're not the way the thing looks in real life. They're just a collection of elements that show the relationships in between. So this circuit that I've shown here on the right is identically the same circuit, even though I've put the resistors in different positions. So what is it that makes them the same circuit, despite the fact that visually they're quite different? Well, the answer is this. I know what happens when I have a closed circuit and a potential difference. The push of the potential difference will cause charges to flow. So positively charged particles will come out of the 9-volt battery and encounter this 1K resistor. They go through. The 1K resistor doesn't stop them. It doesn't even slow them down, really. It just changes the rate at which the charges flow. So they flow into the 1K, they flow out again, and then they immediately flow into the 2K, and then out again, and come around the circuit back to the bottom of the 9-volt battery to be pumped up again by the chemical reaction inside the battery so that they can make the circuit again. Remember, when I complete the connection, when I complete the circuit, the current happens all at once, continuously, everywhere. Wham! There's a current. So the distinction I'm making here is that the current goes into the 1K, out of the 1K, into the 2K, out of the 2K, which here on my right-hand circuit is exactly what happens. It comes out of the 9-volt and goes into the 1K, out of the 1K, into the 2K, out of the 2K, and back to the 9-volt battery, because that's the distinction. Resistors connected in series have the same current. That's how they're alike. Not the way the circuit appears when you write it on paper, but that fact that the series combination has the same current throughout. These two circuits are identical. If there was only one resistor in the circuit, if I had a battery, one resistor, I would use Ohm's law and I'd be able to work out everything. But now that I have a second resistor, I have to do a bit more thinking to try and work out how I should handle the instance of resistors in series. So what I'll probably do to investigate it is go into a laboratory and do an experiment where I measure currents. And so I've expanded the circuit a little bit. It's the same circuit. I have a 9-volt and a 1K and a 2K. But between each one of these resistors, and on either side, I have an ammeter which is measuring the current. Remember, the ammeter has an internal resistance that is very low, So it doesn't disturb the situation at all. And they're a little bit tricky to read because they're small on the image, but it's 3 milliamps, 3 milliamps, 3 milliamps everywhere. All at once, 3 milliamps. Do not make the mistake of thinking that the current is large and goes through the 1K and then the current is less, goes through the 2K and then the current is less. That would be a mistake in your thinking. The current is 3 milliamps everywhere. But why is it 3 milliamps? I can use Ohm's law to work out what the resistance seems to be. That is, instead of looking at this as I do in my schematic as two separate resistors, I wonder what it looks like from the point of view of a charge that is being pushed off the battery. That charge, when it steps off, considers all of the resistance all at once. It doesn't wait till it gets to the first resistor and then behave. It behaves right off the bat because the charges that flow and make up the current in the circuit, big air quotes, know how much resistance there is. Well, I'm going to take this qualitative idea and write it as a quantitative idea by writing an equation that describes it. Now, Ohm's law is true. I'm going to use some Ohm's law here. But I'm going to stir it around to see if I can find out what the equivalent resistance is. That's what I mean when I say the resistance that the current sees in the whole circuit. We call that the equivalent resistance, and here I've called it Req. That's going to happen a lot. Well, according to Ohm's law, V is equal to IR, so R is equal to V over I. Well, I know that I've got 9 volts of resistance. That's what my potential difference is, because that's the value of my battery. I've measured in the laboratory that I have 3 milliamps, which is 0.003 amps. So according to Ohm's law, this circuit seems to have 300 ohms of resistance, or pardon me, 3,000 ohms of resistance in it. That is 3K. And very easily there, suddenly I have my answer. And it's a very sensible one. That when I make a circuit with a series combination of resistors like this, the total resistance that I get is quite simply the sum of the resistances. Now you might say, I would have guessed that when you add more resistors in, you get more resistance. Well, that's true, but with a little careful investigation, I've made sure that it's experimentally true and that the arguments are quite rational, logical, and scientific. Indeed, when I add resistors in series, the equivalent resistance is the sum of the resistances. So simple and so straightforward. You'll notice here in my equation that I've written R equivalent is equal to R1 plus R2 plus ... because I can add more and more resistance in series. And the more resistors I add on, the larger the resistance gets, which is quite sensible. Just adding resistance, adding resistance. In fact, if I were an engineer creating some very sophisticated technology and I realized that my circuit didn't have enough resistance in it, the way that I would increase the resistance of my circuit is to find some place where I could put a little bit of resistance in series, and that would increase the amount of resistance that I have. But that's not the only way that I can organize my resistors. This situation is different. Here you can see in my left-hand diagram, I have a 9-volt battery, and I have my 1K and 2K resistors, but I've hooked them up, so to speak, differently. And they are not in series. The reason why I say that is because in order to be in series, they would have to have the same current. Look what happens if I start here at the 9-volt the 9-volt battery, and I go over the top here and I've got some current and the current's going. The current comes to this junction here at the top of the circuit and splits into 2 parts. Now, if the resistances were equal, I might imagine that the split is equal, but the resistances are not equal. You know, there's a common expression, the path of least resistance. It refers to this. When the current comes from the battery and arrives at the junction at the top of the circuit, it splits, but not equally. More current goes through the path of least resistance, and less current goes through the path of greater resistance. Path of least resistance does not mean zero current goes through the path of higher resistance. It just means more current goes through the least resistive path. So these two resistors do not experience the same current. They are not in series. They are, in fact, in parallel. Now, I will concede right here that this situation is a little bit more abstract because it's not the currents that's the same here, but the voltage. The potential difference across each one of these is the same. Imagine for a second that I remove my 2K resistor. If I just connect the 1K to the 9-volt battery, I'll take the top end of the 1K and connect it to the top of the battery, the bottom end of the 1K and connect it to the bottom of the battery, and then I wouldn't have any trouble convincing you that the potential difference on the resistor was 9 volts. It's connected to a 9-volt battery. I could do the same thing with the 2K, and indeed, here in my left-hand diagram, that's the situation. I have a 1K resistor that is directly connected to the 9 volts, and I have the 2K that is also directly connected to the same 9 volts. Does that mean that they're just two separate circuits, one laid on top of the other? No, unfortunately not. It turns out that the parallel combination of the 1K and 2K resistor looks, air quotes again, a certain kind of way to the 9-volt battery. And I want to work out what the current is. By the way, the circuit that I've shown here on the right looks very different, but it is exactly the same because the current that comes out of the 9-volt has to split at the junction, and so they don't have the same current. They are, in fact, in parallel. The name parallel can be a little bit deceiving because here the 1K and the 2K are on parallel lines. Oh, so they must be in parallel. And the 2K and the 1K here in the right-hand diagram are on parallel lines, but instead of vertically parallel, they're horizontally parallel. That is not the definition of a parallel combination. Parallel combination is same voltage. The fact that they exist on parallel lines often is aesthetically true. It looks that way, but you have to be careful. When circuits get complicated looking, it can sometimes be a bit deceiving. I'm not going to burden you by drawing you circuits where it appears that things might be in series or parallel and it's hard to tell, but it can be a little bit iffy. Now, if there were only one resistor, I could use Ohm's law to work out how much current is going to flow out of the battery. But I don't know what the battery sees. I don't know what it looks like downstream. And when the current appears, it's going to appear everywhere all at once at the speed of light. So I have to figure out some way. Well, the first thing that I'll do is take it into the lab and make some measurements. Just like the first time, I'll take this circuit that appears here on the left, I'll break it down and stick some ammeters in and see what happens. You see, I've used my 3 ammeters, but I've used them to measure the current that comes out of the battery. And I've used them to measure the current in the 1K resistor and the current in the 2K resistor. A little bit hard to see from your point of view. So let me tell you that this is 9 milliamps in the 1K resistor and 4.5 milliamps in the 2K resistor. And that matches my expectation because I believed that since the 1K resistor is less resistance, that more current would flow through the 1K than flows through the 2K. And indeed, it turned out to be true. 9 milliamps, 4.5 milliamps. How much flows out of the battery? A very curious 13.5 milliamps. So I can't just add the resistors together. It's a different amount of current. It's a different amount of current. As a matter of fact, it's a lot more current. If in the series combination, I got 3 milliamps of current. Now I've got 13.5 milliamps, as if the resistance of the circuit is actually decreased when you hook up the resistors this way. I'll tell you another thing. In the 1K resistor, I observe 9 milliamps. In the 2K resistor, I observe 4.5. That adds up to 13.5, which is no surprise. When the 13.5 comes out of the battery and reaches this junction, it splits into 2 parts. But I don't lose current, I don't gain current. The current in the branches has to add up to the original current. Because I've split it, there's like a conservation of current there. When I split it, but it still should add up. So 9 plus 4.5 is 13.5. This is trickier to make an equation out of, and the equation is not so sensible. Well, I guess from a scientific point of view, it's completely sensible, but it doesn't match your expectation. You might not guess it. Here's how I'm going to find out the equivalent resistance that this battery sees so I can explain why it's 13.5 milliamps that comes out of the battery. I'm going to take that idea of what happens at the junction and write it as an equation. The current that comes out of the battery, which I'm calling I, is equal to I1, which is the 9 milliamps that runs through the 1K, plus I2, which is the 4.5 milliamps that runs through the 2K. Now that's all well and good, a very true statement. The current splits. I've written a thing that is physically true and everybody agrees. But according to Ohm's law, V is equal to IR. So I is V over R. So in this equation, I'll call V over R equivalent, the resistance that the battery sees. I is V over R. Well, I1 then would be V1 over R1. I2 would be V2 over R2. But both resistors have the same voltage because they are connected in parallel. Parallel means same voltage, means 9 volts, 9 volts, 9 volts. Well, if they all see the same voltage, then V cancels V1, cancels V2, and then 1 over R equivalent is equal to 1 over R plus 1 over R2, 1 over R1 plus 1 over R2 plus 1 over R3, as many resistors as you connect in parallel. It's weird to have an equation that leads off 1 over the thing is equal to. Actually, I'm fibbing a bit because to a physicist, that's not really a strange circumstance at all. But it might be unfamiliar to you. So what I'm going to do is combine these fractions, 1 over R1 and 1 over R2, so I can write one equivalent law. When resistors are connected in parallel, the equivalent resistance is R1 times R2 divided by R1 plus R2. Obviously, not as simple a relationship as resistors in series. Everybody likes resistors in series better, R1 plus R2 plus R3 plus R4. This is a more complicated equation, and it has a particular feature. When you calculate the equivalent resistance of resistors in parallel, the resulting equivalent resistance is always less than either R1 and R2. Adding resistors in parallel reduces the resistance of the circuit. So if I'm engineering a complicated circuit and I find myself with too much resistance the way that I've designed it, I'm going to be looking for a way to insert some resistance in parallel to reduce the overall resistance. If this is my equation for equivalent resistance in parallel, then I should be able to use it to prove that 13.5 milliamps coming out of the battery makes sense. Well, what is the equivalent resistance of these two resistors connected parallel to one another? Well, it's easy. The equivalent resistance is R1, R2 over R1 plus R2, which is 1K times 2K divided by 1K plus 2K, which is obviously 2/3 K. Well, 2/3. I'm not going to deal with the fraction. So it's 0.667 K. At that point, it doesn't make sense to write K because K is thousands. That's 667 ohms. Of course, I've rounded that. It's 6 repeating forever and ever. But 667 ohms of resistance. So if I take my 9 volts and divide it by that equivalent resistance, I get 13.5 milliamps, exactly what I expected, which is a greater current than when the resistors were connected in series, because connecting the resistors in series increases the resistance and therefore reduces the current. And connecting the resistors in parallel reduces the resistance, thereby increasing the current.
Mm-hmm.